Testing, sound. Yes, there's sound here. Hello, good afternoon. Um, Good Saturday afternoon to everyone. How are you guys doing? I, I'm still having problems with my YouTube streaming. I don't know what's going on, but I still have a 0 in concurrent viewers. And it's not updating. So I don't know how many people are right now watching this. I don't know who you are. So if you want to say hi and or something. Hey Monique, how are you doing? Good afternoon again. So so yeah, I have no idea how many people are watching this right now. So okay. So this is part 2 of the live stream that we started this morning in my previous channel, my personal channel. Remember, for everybody watching this, we are... Oh, Kartik, Ipsita, Rafael, Reynaldo, Anshul. I don't know if I've seen you before. Hi, what's up? Rodolfo, what's up, Ben? Um, so this is going to be part 2 of the YouTube stream that we started this morning, where we were taking a look at modeling the Calatravas umbracal in Valencia, and we were doing this in pure C sharp, in C sharp scripting within Grasshopper. I did not finish the exercise. We still have to design all the ribs, we still have to copy all the ribs and clone them, we still have to generate the profile beams and output them as well, and then the tubes, the surfaces. So hopefully that's not going to take us very long. I think we're like most of the way there. So I think we probably want to wrap this up a little bit earlier today, because it's also super nice out there, and I would like to enjoy the Saturday, and you guys probably want to enjoy it too. I want... Well, if you are here, you probably don't know that I'm just doing this every live stream. So if you've heard this before, I'm sorry, but we're just want to say that we're moving permanently into this new channel, Parametric Camp, where we are right now. If you are coming from Garcia del Castillo, feel free to subscribe and click, etc., and all the goodness. And we also have a Discord that we're using as an offline forum for conversations and introductions during the week. I'm actually starting to get to know a lot of you, and I see most of the names that I see in the chat are already familiar faces from the Discord. So if you're new here, please feel welcome to go to the link that I posted all the way at the beginning of the chat and accept the invitation and join the Discord. Introduce yourself, tell us where you're from, what brings you here, why are you interested. We take suggestions for the live stream, so it's great. Hari Prasad, good evening, good afternoon. Is that a hand sanitizer emoji? Oh god, crazy times we live in. Anyway, so where was I? Where were we? Where were we? We were here. I had just explained that instead of generating the rifts parametrically for all the spans, since the rifts are the exact same ones, it's a bit cheaper to just generate them once and clone them in the direction of in the spanning direction, which is what we're going to do here. We will do a little bit of like nice magic with data trees, just because I want to be super ordered in how I spit out the ribs. So we're going to do a little bit of trickery and magic with that. So that's going to be cool. And then we're going to do the beams, and then that's going to be it. And I need to remember to record the introduction. I always forget. So please remind me, and then we can do like a little bit of Q&A and social and chat, etc., etc. Okay. So shall we get busy? All right. Okay. Let's do it. I don't know who was this morning that recommended to do the Kengokuma bridge. exercise. I'm thinking about it, and the more I think about it, the more I like it. So I think that's going to happen very soon, if next week or the other one so soon, because I think it's a simple exercise, but a really nice and really interesting one. Um, and yes, I'm like, so we may not do exactly the bridge. We may do, we may really hone into this pyramid structures that King Okuma does, where he stacks all these bars. I think that is super interesting, and maybe we could do like a part two. Who recommended this? Um, was it Rafael? Rafael, where is you, or was it? I forget. Um, and maybe it could be interesting to do. Maybe it could be interesting to do. Uh, even the notching. Even we could do the notching. That would be like an advanced version of it. That could be really cool, actually. That could be really cool. Anyway, the more I think about it, the more excited I am. So we may actually do it. Okay. Mm-hmm. Okay. So where were we? Yes, we were here. Okay. And we were going to finish off the ribs and clone them. Okay. So let's get to that. Uh, Thank you, Parastorm. Thanks to you. Thanks to you guys for being here. I mean, I do this because of the community and because of I have a lot of fun doing this as well. What is your real name, Parastorm? We always refer to you by the by your YouTube channel name. I guess that's it. Um, so no, but no, wait. You introduced yourself in the. Didn't you introduce yourself in the Discord? I think you did. Okay. I have to take a look at that. So, but I think we actually saw your grasshopper tutorials, didn't we? Anyway, um, we can move that conversation offline. Um, okay. So here. Mm-hmm. Okay. Mm-hmm. Mm-hmm. Um, okay. Yes. So how are we? Yes. Okay. Before we go on, let me change a couple things of what I've done so far because we want to be very rigorous about generating the first family of ribs, the one on the left of the span, and then generating the second family of ribs, the one on the right side of the span, and then use those as the base that we're going to be copying and moving around. Okay, so I'm going to change a little bit of the naming. I'm going to refactor my variables, and here I'm going to say these are going to be the left span ribs. Okay, and so this is going to be, I'm going to have to change this here. This I can take away, and then I will then have to also generate the ones on the right hand side. So what I could do is I could take the curve, the first curve that I have copied and moved here to the right side. I could take that one, subdivided by points, and then like do the ribs. But since those points are actually the exact same ones as the one that I have here, then I can basically just take all those points, move them to the right, or create new points on the right hand side at a distance of span, and then just use those as the base. So for example, arch curve points, this I'm going to refactor this to be on the left, and this arch curve points on the left, and then I can, for example, now I'm going to take it back. I'm going to create a new curve on the right, and I'm going to subdivide that one, and then I'm going to, no, No, I'm not. I'm going to stick to what I said. Okay, so I'm going to say now points arch curve on the right. Okay, and this is going to be equal to a new point array, which is going to have the same amount of points that are currently here on that are currently here on the array of points on the left. So I'm going to create an empty array, points on the right, and then what I'm going to do is with a for loop, I'm going to populate with this array with copies of the points that are on the array of points of the left arch. This is very hard to explain. But I'm just going to, for those points, I'm just going to increase the x coordinate by a distance of d. If you remember the diagram, d is the distance between spans. So with a for loop, is less than however many points are here on the left. Okay, and then I++, and then here I'm going to say 0.3d p is going to be equal to a new 0.3d, where I'm going to take this point, the x coordinate, I'm going to take the y and the c coordinate, but then to the x coordinate, I'm going to add the distance of d, the distance of the span. And then after I do that, I'm going to say the point in location y in the array of points of the right is going to be equal to that point that I just created. Okay? Let's see. Does that make sense? Is that looking right? So let me run this. I have an error. What have I done? Okay, arch curve points that not exist, 143. So when I was refactoring this one, I have to remember to refactor this, and this also has to be refactored there. Okay, and then you can see that I have here my points on the left. Okay, on the right. That is looking good. And then now that I have the points on the right, I can say, well, let me create a for loop. Let me create an empty array of an empty list of line elements. That's going to be right span ribs. It's going to be a new list of elements. Okay, and then with a for loop, I'm going to go over all of those elements. So that's going to be arch, all the points on the right hand side, and then I++, and then here I'm going to say I'm going to create a line. L is going to be equal to a new line between 2 points. Which 2 points are those going to be? Those are going to be first the first point on the right arch point, so this one, okay? And then the second one is going to be the points in the middle arch. Those were here, middle arch curve points. Also, the one in the same position, the one in position I. And after that, I'm going to take this and I'm going to add the line that I just created, L, to this array. Let me see if that works. So right span ribs. Okay. All right, it's looking good. Okay, great. So now finally I have my left span ribs and my right span ribs. Okay, I have the two families. So now what I need to do is I just need to create a data tree, and one by one for each one of the spans, start copying and moving all these ribs in sequence. Okay, let's get that going. Okay. Okay. So how are we going to do this? How? Well, just like we did before, we have a data tree, and then for each data tree, we take the for each span, we take all the left ribs and the right ribs, we clone them, we move them, and then do line elements have cloning? Let me check that. L dot duplicate curve, copy, clone, closest point equal extend through box. Good. I knew this was gonna happen. Okay, so we can do this, and then we can just say duplicate curve. Doesn't line, it doesn't belong to geometry base. Interesting. So how can I duplicate? Wait, so if line is what is line? Is line a struct? If it's a struct, then I think we can just it is a struct. So how can I can clone a struct? C# cloning structs. To copy a struct, create a new copy of the object and assign the copy of the object to a separate struct instance. Tip copy of a struct. It's not possible to introduce or force your own copying procedure for that. You can introduce your own clone method. Copy does not have because user reflection is the use of binary former. No. Structs are different than classes in that they use they have different rules about how they are allocated in memory and how they get passed between functions. So if you copy a struct, you see structs are value types and classes are reference types. If you copy a struct, it assigns the copy of the object to a separate struct instance. So let me try one thing out. Line foo equals a new line between 0, 0, 0 and 1, 1, 1. Line bar equals foo. If I take point at tenors curve, point at length, extend distance to, so we can't really. Interesting, because they're just lines, it's going to be more difficult to. So if I do this, does foo change? Foo, does the point in foo, is that a reference or a copy? It doesn't change, so it is a copy, so I can just copy them. So do I have something like class is going to be equal to new line So can I just add to this a new vector 3D? This is a little complicated. This is over complicated. Print bar from to string. Am I complicating things around here? I think I am, yeah. Well, this is how we started, so we're gonna have to do this. I hope I'm not gonna mess this up. Okay, so where was I? I was saying that we're gonna do a data tree, and then we're going to copy everything, and we're going to okay. All right, so let's create the data tree. Okay, I'm going to create the base briefs here, and then I'm going to create, okay. Let's get to it. So I'm going here to create the ribs data tree, and then very simply, I'm just going to go ahead and create, for example, a data tree of line objects here, which I'm going to call rib lines. Okay, and then this is going to be a line object. Okay, and then we need to now create a for loop, which is going to iterate over all the spans that we have. So that's going to be equal to I is less than number of spans, and I plus plus all the ribs on the left. We have to duplicate them, and then we have to displace them. So first of all, I'm going to the distance d, which is the distance between spans, which means that if we're on the first span, I is 0, so we don't move anything, we just copy things in place. If we are on span number and second span, I is 1, so we're going to move things, we're going to move the ribs by distance of 1d, etc., etc. Okay? Now what we can do now is we can say, I'm going to create a list of line objects, and these are going to be left clones. And I'm going to start an empty list here. And here, what we're going to do is we're going to create a for loop where we're going to iterate over all the left spans, all the ribs that we calculated first. We're going to clone them, and then we're going to move them. So that's going to be int j equals 0, j is less than left span ribs dot length count, because it's a list, and then j plus plus, and then here we're going to say line L line clone is going to be equal to left span ribs dot I. Okay, square brackets I. So because lines are structs, that means that this is a copy. Okay, so what it means is that the variable clone is actually not pointing to the value that is contained here, but this, so clone becomes a copy that of the value that we have in left span ribs, and then if we make modifications to clone, those modifications do not affect the original rib that we had here. Okay, so let me show you. So now that we have clone here, what I can say is, in order to move it, lines don't have the duplicate curve. Lines don't have the duplicate method, the duplicate curve method that we've used before, and because of that, we can't really translate them, and they also don't have a translate. And this is also because since they are structs, they do not inherit from the geometry-based class, and therefore they don't get all that goodness. So what we need to do is we need to be a bit more manual here, and what we need to do is we need to take both the starting point and the end point of the line, move them with the v vector, and then therefore that becomes the modification of and the translation of the curve of the line. So here what we can say is clone dot from, and that is the point where the line segment starts, and then increment that location by the vector b. And then we can also take clone dot to, which is the end point of this line segment, and do the exact same thing. Increment its coordinates by the coordinates of vector v. Okay, and we have this now. So we have created a copy of clones here, and once we have that, then what we need to do is we need in the rib lines, we can create a data tree. We can create a new branch. So grasshopper path path equals new grasshopper, like we did before, and then use I as the index of that path, and then go to rib lines and add range in this case, because we're going to add the whole list at once. Add range, and then take left clones, take the whole list, not just one by one, and then add it at the new path that we just created. If I write this, I don't get any errors. It looks well. So let me create an output here that is going to be called rib lines, for example. And as I do that, I'm going to double click here. I'm going to update, refresh this. I may not want to use the rib lines here then, because it's a duplicate name with this. So I'm just going to use, for example, rib axis, for example. And here I'm going to use, I'm going to do that here as well. And then here rib lines is going to be equal to rib axis. I do that, and it looks like nothing has happened. What do we have here? Oh, they're empty. Oh yeah, because I forgot to add. You see, we have the empty structure because I forgot to add the clone. I forgot to add the clone to the list of left clones, and therefore we were doing the process, but those lines were going nowhere, and this line remained empty. So we were adding empty lists to the data tree, and I do that, and it doesn't work because I have misspelled something. Yeah, I said clones instead of clone, and I do that, and ooh, something went not very great. I've only moved these 3 lines here. Let's see what happened. It's probably something with the so left span ribs that count, line clone okay, let me take a look at this. Simon, can you create a curve of degree 1 between points instead of a line? We can do that, but that would create a curve object that is more expensive computationally. It's not as clean, as lean as a line object is. So even at the expense of the code being a little more tedious, I want to keep, because there are straight lines, I want to keep it as the simplest geometry object possible, which is going to be a line. If we were to turn those into NURBS curves, for example, of degree 1, each one of them would be just much heavier because it would have the control points, the nodes, etc., and we don't really need that. So even though it's a bit more tedious, the resulting geometry is going to be much easier and lean to handle by Rhino. So okay, so what are we doing here? Okay, so this is exactly. So for each span, okay, because I'm using I here instead of J. This is a very common mistake. So if I do J, right? Yes. Huh. But it's also, they're not where they're supposed to be. Okay, so console equals left span grips there's something odd here because this should not look like this. Mm-hmm. Can anybody see what am I doing wrong here? Oh, this is I. No, this is that's I. That should be I. And why are they moving? Oh, because it's I plus D. It's I times D. Okay. All right. All right. Okay. Okay. So that was it, and that was here. Okay. Okay. So okay. So we're good. Yeah, this is what happens with coding, trying to code things fast. I am in a nested for loop where I'm using I to iterate over the spans, and I'm using J here to iterate over each one of the ribs. And here in left span ribs, I used I, which is the span iterator, as opposed to J, which is the rib iterator. So if I change that to J, now we get this for each one of the lines, but also you guys can see that they're not exactly where they should be. The first one should be here, the second one here, and the third one here, and there's like an offset, and this is because I also made a typo here. This should be I times D. So the number of spans times the distance between spans instead of plus. So I'm going to change this, and I'm going to have it here. Okay. So that is great. And the tree that I'm pulling out of rib lines also looks great because it's branch 0 and then branch 1 and branch 2. They have all these lines. Okay, so that's great. So this is, let me just fill in for the second, for the ones on the right. So this is going to be super similar. I'm just going to take this and say right clones is going to be equal. Be careful with copy pasting, okay? So right clones, new list, blah blah blah. This should be right span ribs, blah blah blah, and then clone is going to be right span ribs, clone from clone clue, and then right clones add clone. Okay. If I run this, there's no errors, and then I can copy paste this and path, new path, blah blah blah. And actually this is redundant because I already have the path, right? So what I want to do is I want to do here right clones. I want to do this, and then you can see that now we just duplicated the clones on the right, and they have been added to the tree where they should be on. So it on branch 0, branch 1, and branch 2. However, okay, I hope you already know me at this point because this is nice, but it's not as clean as it could be because what happens now is that I have done this very fast, obviously, and now in branch 0, we have first all the lines, all the ribs on the left, and then continuously, without no separation, we have the ones on the right. So if I needed down the road for some reason to make a distinction between the ones in the left and the ones on the right, I don't know, maybe the sun is hidden from a different the orientation, and I want the louvers on one side to be thicker than the other, whatever. I would have to manually go here, divide the list in two, split them, whatever. So since we're here already, why not create a nicer data tree structure where the ribs on the left and the ribs on the right are much easier to see and are already separated in different branches. So what I'm going to do, but I'm going to do it in a different way. You could argue, well, if you're now creating 3 branches, 0, 1, 2, because you have 3 spans, why not create 6 branches, 0, 1, 2, 3, 4, 5, and then the ones that are odd are the ones on the left, and the ones that are even are the ones on the right. We could do that, but that's also not entirely clean. The nice thing about data trees is that the branch allows nesting of levels. So because we have a modular system that has 3 spans, I would like the first level of the data tree, the first number, to tell me which span I am in, and then I would like to add a second level to the branch, a second number that tells me if it's 0, it's the ones on the left. If it's 1, it's the ones on the right, and then have like a kind of like a branching data tree structure, you know. So that's actually super easy to do, because since we already divided that process very cleanly here, what we can say is I can create first for the ribs on the left, I can create a new path, and let me see. So you see how instead of creating I can create a path, an empty path. I can create a path with one index. I can create a path with an array of indices. And then I can create a path copying it from another path. So what I want to do is I want to create an array of indices that represent the levels of my data, of my branch. And I want the first level to be the span that I am in. So that's going to be I. And then the second level to be 0 if it's on the ribs on the left, and 1 if it's the ribs on the right. So let me create an array here. Okay, int path indices. Okay, and this is going to be equal to a new array of integers with 2 elements, and I believe I can initialize it like this. I believe I can initialize it with the value of I is going to be the first value, and the value of 0 is going to be the second one. Okay, and then as I do that, then I can use that here to specify the index, and then let me see if that works. Did that work? Yes, it worked. You see how now here I have the branch. The branch has the 2 indices. The first one is I, and the second one is hard-coded to 0. And if I keep going, the first one is I, and the second one is hard-coded to 0. So now I can do this. I can do a new one where I say, well, path indices before had this value. Now I want to change that. I don't need to declare it again, but I want to change it and say, okay, path indices now is going to be a new array. I'm going to reset it. I is still going to be I, but then this is going to be number 1 instead. And then I'm also going to reset the path by saying, whatever the path was before, change it to a new path with the new path indices that I just created here. As I run that, check this out. We have 0, 0 here. I'm going to lower the number of ribs so that we can, so 10 ribs only. And then we have here 0, 0. It's span 0. So both have span 0, but then 0 is the left. This is very hard to say. But these are the ones on the left. These are the ones on the right. And then these are the ones on the left. These are the ones on the right. And I actually, can I plug in here this thing where, so that I can see. And look, you guys can see we have this branching structure. Okay, so this is representing the structure of the data tree. These are the elements. These are the spans, and this is how they separate between left and right. Okay, so I think this data structure is much cleaner as an output, and whoever was to take this data and start working with it could operate much cleanly with this data structure here. So I find that solution much better and much more pro. So I'm just going to go for that. Okay. Okay. So that was a lot. But I think we're ready now. I mean, we have the whole, we have the whole, we have basically have the whole building already. So now in number of spans, and we have the whole building written in C# script, and then we can just modify the width, we can modify the height of the elements. Oh, this is actually quite cool. Huh. And then we can make them, the spans, we can make them wider. This is like the Madrid airport almost. This is kind of cool. And now what we need to do is, in order to complete this, what we need to do is we need to create for example, if this was competition, we will need to create solid object surfaces so that we could render this, as opposed to the lines that we're doing here, which could be used, for example, as an axis for the structures. So let's go ahead and create the variable thickness beams for the arches and create the tubular pipes for the lines. Okay, let's do it. Okay, how did you like the data tree? Did you guys know how to do this? Was it good learning practice? Okay, I'm going to load here. I'm going to load here the diagrams for here. I'm going to load here the diagram for the beam. Okay, I'm going to, yeah, this one here. Okay. I'm going to save this. And what else? So, and then how are we going to start? Let me remind myself, how did we do this? We divided how did we do this before? We divided the curve into a bunch of points, and we hard-coded this to be 30. That was a little arbitrary, but whatever. So perpendicular frames, and we found those frames, and then we created rectangles with variable thickness. And then based on the rule, okay, and then we just did a sweep with one rail curve. Let me look that up before sweep one rail constructor. Initializes a sweep one rail class. What does that mean? Ooh. Graphics, blah blah blah. Sweep one rail. Okay, so here, sweep one rail, angle, close sweep, tolerance, set to roll like top, performance, the rail curve, and the cross sections. And the cross sections are of what type? They are curves. Okay. Okay. And then we get view reps. Perform sweep. And then perform sweep. We get the curve, blah, 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 rail, cross sections, and we get an array of B reps. Okay, we can do this, I think. So what are we going to do? We're going to take the base curve. We're going to subdivide it in points. We're going to create cross sections, and we're going to do a sweep rail. And for the time being, those sweep sections are going to be the same. And then we will explain how to create rectangles where the proportions of the beam are slightly different. Okay. Okay. How can we create a rectangle on a plane? That's easy, right? Okay. We have Rhino geometry. Do we have rectangle here? Rectangle 3D structure. Represents the values of a plane and two intervals that form an oriented triangle in 3 dimensions. Okay. And can we turn this into a NURBS curve? Yes. Okay. So rectangle 3D represents a values of a plane and two intervals that form an oriented rectangle in 3 dimensions. Okay, that's a little complicated. Maybe we can start with a circle. Is there a circle on a plane here? I don't think there is, no? Circle structure? Okay. Represents a circle in 3D. The values are used, circle, plane, initializes a circle on a plane with a given radius. Plane and radius. Okay. Okay, so yeah. So we can start with a circle. Okay. And then D1. Okay. Okay. Before we start coding, as usual, it's very important to to refresh our thing, to refresh things in our head and to have a clear picture of where we want to go. So let me refresh what we did in the last video. We had because the beams had a variable section, so the section was much larger here close to the base than it was all the way up there in the top, because there's more stresses. There are more stresses coming near the base. So we wanted to mimic that. So, and we came up with a very simple numerical rule to figure that out. But what we're going to do here is, because it's going to take quite some code to put this together in C#, what I want to do is I want to do first a very simple example where we just take the curve, we subdivide it into all those sections in all the planes, perpendicular frames, and then we just place there a very simple section, like for example a circle, and then we create the sweep. With that circle, curve, just for the sake of learning how to create that surface and that B-rep. And then once we got that under control, then we will figure out how to actually turn those circles into rectangles, and how to have those rectangles have a dimension that is proportional to how far away they are from the base. Okay, so let's do this in a very stepwise manner. Let's do the simple part first, which is the sweep, and then let's implement after that the numerical rule to have the rectangles vary in the section. All right, I also forgot to look up perpendicular frames. Vector, curve perpendicular, get perpendicular frames. Okay. Okay. Um, and then we need the list of parameters, which we can probably get from um, curve divide by count, which we used before. Divide by count method, and it gives me the doubles. Yep. Okay. Oh, sorry, I was I was still in the diagram. Okay. Um, so let's get started. We're going to add some comments here. This is really good practice. Create create main arch sweep brep. And what I'm going to do is the first thing that we're going to do is we're going to take the arch, the curve that we created before, and then we're going to subdivide it in perpendicular frames. How are we going to do that? Well, first let me figure out where that curve was. Arch curve was the base, so I'm going to bring this here. That was the name. And then what we need to do is we need to subdivide this into perpendicular frames. So there's got to be something in Rhino common, and I was looking it up before, and we have the curve subdivide get perpendicular frames method, which gives me a collection of perpendicular frames along the curve. So that's probably going to work. So what I'm going to do is, and the return type is going to be a bunch of planes, which is exactly what I want. So let me go back here and let's say plane perpendicular frames main arch. That's going to be equal to arch curve dot get perpendicular frames. Okay, and what this function needs is an I enumerable, which is just a way of saying that something that is a list-like element, like an array or a list, of the parameters. So it kind of sucks because I can't really tell. It just gives me to subdivide this in 30 different frames. So I need to give it the parameters at which I want those perpendicular frames. So we need to do something before. What we need to do is we need to figure out for this curve, we need to subdivide it in however many elements and then get the parameters of the curve at those subdivisions. So I'm going to put this on hold here before, and then what I'm going to do is I'm going to rely on this other method, curve divide by count. And if you see, this takes how many segments and whether if I want to include the ends or not. And the return type is an array of doubles that are the curve parameters at those divisions points. So what this does is, given the curve and given how many segments I want to divide, it gives me the numerical values of those parameters along the curve. So this sounds really useful. So I'm going to say create a double array of main arch, for example, subdivision parameters. The names of these variables are ridiculously long. Please don't do this at home like this, okay? So what I'm going to do is arch curve, and I'm going to say divide by count. And here, how many segments are we going to take? I don't know. We could have this as an input, so we could let the user decide, but we also don't want the user to be able to input like parameters that we don't like, that they're too low for perhaps. So I think for this one, I'm just gonna hard code in a number. That's not great practice in general, but I also don't want the user to be able to input a number that would not work. So I'm just gonna go, for example, for 30, which I believe is what we did in the vanilla exercise. And then I want to include the ends, that is true. And this way I will get all these parameters. Now that we have that, I can use these parameters here. And then let me just output all these planes to see if they make any sense whatsoever. I'm going to run this, and it looks good. It looks like these planes are more or less evenly distributed, and I like that there is one exactly at the center of the curve because I want that kind of symmetry. I want this to be exactly the size of D2, just as we had in the diagram. So things are looking good. Okay, now I'm going to use these planes to generate circles. For example, how am I going to do this? I'm going to create a circle array of sections, and this is going to have the same size as this, as the number of planes that we just created. Okay, and then I'm going to go ahead, and with a for loop, I'm just going to create as many circles as frames that we had. So this is going to be equal to sections dot length, and then I++, and then here I'm going to say for each one of the planes, so plane PL, give me the plane that I want. Okay, and then circle C is going to be equal to a new circle that I'm going to create with the base plane and the radius. So plane and then the radius, I think I'm going to use lowercase w, which I think is one of the input values, but this is going to be a placeholder. I will change this later. And then sections I is going to be equal to that circle that I just created. What does that mean? Is that working? Let me see if I can output all these sections. Okay, and it looks good. I just created an array of circles, one per plane. Okay, and I think we should be good now to create the sweep so that we can see how that works. As usual, it's a very good thing to go to documentation. So we can see here that sweep is not an operation, it's actually a class. So what that means is that sweep one rail, it's an utility class. So you cannot really create a surface by just saying surface.sweep one rail. There's actually a full class that is dedicated to handling how sweep rails are created. So for example, if we go to the constructor, as we saw before, there is a tiny example here of how to do that. So it looks like, this is the first time I'm doing it myself. It looks like we have to create a new instance of sweep one rail. Then we have to define some parameters. Okay, and then once those parameters are defined, then we can perform the sweep, inputting the rail curve that we want to use and those cross sections. Okay, so I'm going to copy paste this here. I'm going to copy this in my code so that I can use as a template. Okay, and I'm going to rewrite it so that it looks more like, so that it uses the variables and all the stuff that I've been working with. So how are we going to start? So I'm going to say sweep one rail, sweep operation is going to be equal to a new sweep one rail object. Okay. Then the next thing is I'm going to set some. I'm going to call this sweep. Then I'm going to set some variables. So for example, angle tolerance in radians. I don't know what this really means. We could look it up, but maybe do we have access to the doc property? Yes, we do have access to the document property, so we're going to just keep it like that. Sweep, is this going to be a closed sweep? That's going to be false. Is this going to be a sweep tolerance? Is going to use also the document tolerance mode. and then sweep is going to be set road like top. I have no idea what this means. We could look it up, but I'm just going to copy it. If you're interested in really tweaking this, you're more than welcome to look at the documentation. And then now what's interesting is that we want to do perform sweep. Okay, so sweep, perform sweep, and it doesn't look like perform sweep on its own exists anymore or is accessible to us. Let's take a look at that. Perform sweep curve, and this is missing the documentation. Perform sweep rebuild, perform sweep refit. Is supported in Rhino for Windows 625? 625. Am I on Rhino 625? Where is Rhino 621? So maybe I don't have access to that functionality yet. Is that possible? I don't know. Perform sweep. Let's just try. Yeah, because it actually shows up. So maybe it was just not showing up on the panel, which is kind of weird. But anyway, so let's take the arch curve as the rail curve, and the cross sections are going to be the sections. Okay, and this is going to return an array of B reps. So an array of B reps. So that's going to be, what am I going to call this? Arch, main arch surfaces, for example. And then here, I'm going to output that, see if it works. Okay, it is not working. So something is going. The best overloaded sweep rail preferred has some invalid arguments. Cannot convert from Rhino geometry circle to Rhino geometry curve. Okay. Okay. Let me take a look at this. Do we think the problem is that these are circles, or do we think that this is just sweep, perform sweep, rail, cross section, cross sections, rail, cross section, these cross sections? Huh. Okay. So maybe this doesn't really sweep or perform sweep, and then curve rail, curve cross sections. Course curve. Don't curve rail, that's going to be arch curve. So if I do this, if I do two curves, this works, but that's not what I want. If I do sections, I think, okay. Let's say I did curve here, and then I did two nerves curve, for example. Is this going to work? Cannot convert. Cannot implicitly convert type. Sorry, here. I need to change this too. Okay, all right. So it looks like, yeah, straight circle because circles are structs, I think. Yeah, so that's why it cannot. Yes, I think that was the problem, probably. Mm-hmm. Let me take a look at this, at circles. Circle structure, yes. So they're not curves. They're not really. Okay, so that's probably the problem. Okay, sounds good. Mm, okay, so some comments. Control S. Thank you for that reminder. Do you have to declare a brep to use it? Yes, usually you have to. Can you use coerce curve? What is? I'm not sure what coerce curve is, but I think what you mean is that what we just did. We have to turn those circles that are basically numerical entities. We have to turn them into nerves curves that are that inherit from curve classes and can be used for lofting operations. For the circle to curve, exactly, that's what you meant. Don't you need a list of sections instead of an array? Nope, we actually don't, because this thing here, where is this? Where are you? Perform sweep. Perform sweep takes an I enumerable. What that of curve objects. What that means is that I enumerable is technically an interface, and what that means is that this method will accept anything that can be iterated through. That has an iterator interface, like this one. That applies to arrays, and that applies to lists, and that applies to a lot of other objects in the world of C#. So anything that you can, it's not exactly like that, but anything that you can use a for loop to go through and fetch all the elements individually, that can be fed into this argument here. Does that satisfy your question, Reynaldo? Is that good? It just has to contain curve objects. And I think that's the problem that we were hitting, because Rhino cannot automatically convert from circles to curves. Okay, so let's go back to this. Yes, so the problem that we were hitting is that Rhino was not able to accept here, was not able to accept an array of circles, because it needs an array or a list of curves. And it just so happens that even for us, circles can be thought as curves, but the circle structure is actually is actually a numerical structure that doesn't inherit from geometry base, or it doesn't belong to the curve class. So the conversion is not automatically. So the only thing that we need to do is that we can still work with the circles and create circles, but before we store them in this array, we have to turn them into nerves curves. So the first thing that we can do is we can change the type of the sections array, and instead of being an array of circles, it's going to be an array of curves. So that's one thing. And then the other thing is here. So if we run this, you see that in line 203, we cannot save a circle inside of a curve array. The only thing that we need to do is we need to take the circle, and before we save it into this array, we need to turn it into a nerves curves. So we can use the method called toNervesCurves, convert it, and then save it into that array. As we do that, I can now click here, and I can see that nothing shows up. But if I now take main arches and I output it in the console output, you can see that I now have my pipe that has been swept over the rail, which is the base arch here. Okay, all right. So I think we're good. I'm going to remove all this nasty code here. So I think we're good now for as how to create a sweep, and I think we're in a good position now to start looking at how to instead of using plain circles, how to create rectangles and how to change the dimensions. So I think the first thing we're going to do is right away we're just going to create rectangles here. So we're going to substitute here. Instead of doing circles, okay, I'm going to say rectangle 3D. I believe R is going to be equal to a new rectangle 3D. And then this is going to take a plane. So that's going to be PL. And then the width, which I believe, let me take a look at the diagram. I believe the width was W. And we're just going to use, for all of them, we're just going to use D1. And we will take a look at how to change that programmatically. So now the width is going to be W, which was one of the inputs, and D1, which was another one of the inputs. And then here, we're going to take the rectangle and we're going to turn it into a nerves curve as well. Before we and then I'm running this, but I'm not seeing anything. Oh, because I did. Okay, and we can see that we have the arch, but the arch is not entirely what we would want to. First of all, for us, the width and the height are flipped. That's one thing. But also, you can see that the arch is here. And because we're using width and height, the rectangle is not applying that width and that height at the center. It's applying it offset. So it's taking the center, the line is taking it as the corner of the section. So what that means is that I'm going to have to work a little bit with my inputs, and I'm going to have to look. Let me look at other ways of creating rectangles. So if we look at the overloads, of what a rectangle accepts, you can see that it takes a plane and then two numbers, width and height, but it can also take two intervals for the width and the height, as well as 2 points in the corner. The points are going to be really messy to do, but if we use intervals, we can create an interval that goes from minus half the width to plus half the width, and to minus half the height and plus half the height, and therefore we would have the rectangle centered around the rail curve. So let's do that. So I'm going to say interval width is going to be a new interval that is going to go from minus 0.5 times width and 0.5 times width. That's one thing. Then the interval for height is going to be minus blah 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 d1 plus blah 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 d1, and then I'm going to use these two. I'm going to use PL, width and height. And as I do this, let's cross fingers. Yay! You guys can see that now the section is perfectly centered around the rail, but width and height are flipped. So I don't know whether if to change the numbers or to change the where these guys go. I'm just going to do D1 and D1 and W and W, and that's how I'm going to switch things around. Okay, and so that's looking great. Wow, great. So we're almost there. Now the only thing that we need to do is we need to figure out the numerical rule to make the sections decrease as we go up. Okay, and that's also going to be super easy, as opposed to how we did in vanilla grasshopper. That was a little convoluted, but here it's just going to be a couple of multiplications and divisions. Let's take a look at that. Okay, and the way we did that was we had the height of the arch, we calculated the difference between D1 and D2. So how much the section decreased, and then we calculated from 0 to 1 how far off the center of the section was. The center of the section was from the base. So if it was here, then the section was like at 0, but if it was here, it was at 1, and then it had all these in between steps. And what we do is like we decrease the section by a factor that is proportional to how far off it is. So I'm going to explain that. Just a refresher, what we're going to do to implement that rule is we're going to implement a rule where for each one of the sections, so all the way from the bottom to the top, for each one of the sections, we're going to compute in relative terms, so from 0 to 1, how far off the center of each one of those sections is from the base plane where the building is sitting. So if the plane is at the bottom, then the value of that proportional distance is 0. If the plane is all the way at the top, then the value is 1. And then all the planes in between have proportional values 0.1, 0.2, 0.3, etc. Okay? And then we're going to use that numerical value to decrease the section by that factor. So we're going to calculate how big the section is in the bottom, how big it is in the top. We're going to calculate the difference in section, so how much it decreases. And then we're going to multiply that value by 0, 0.1, 0.2, 0.3 to start decreasing the value of the section over the height. Okay? So this sounds much more difficult to explain than to do. So for example, let's say here, where I'm going to calculate double section difference is going to be equal to D1 minus D2. So that is how much the section decreases from the bottom to the top. Okay? And now what I'm going to do also is I'm going to here for each plane, I'm going to calculate something that I'm going to call the normalized height. Okay, so that is going to be from 0 to 1, how far off this is from the ground. And that is going to be where that's going to be the C height of the base point. So where the base point, so that's going to be the C height of this one, and the C height of the where the plane is right now. So plane dot origin z minus base. So the C let me say this again. The C coordinate of the origin of the plane minus the C coordinate of the base point. So that's going to be how far the center of this plane is from the ground. But it's going to be in absolute terms. It's going to be in whatever units we're working with. But to make it proportional, what I want to know is, what I want to do is to take all of this and divide it by the full height of the building, which, if I remember correctly, is h. So what that means is that if because h is, I don't know, whatever, 10 meters, if the height of this point is 10 meters over the ground, then this point is going to have a normalized height of 1. But if this point is 0 over the ground, then its normalized height is also going to be 0. Now once we have this, we can compute. How much do we have to decrease the section. So double is going to be the section, the new section height is going to be equal to D1, so the base, minus the section difference, so how much is the difference, times this normalized height. Can you guys see this? So we start with the base, and we start, because this becomes greater and greater and greater as we go up in the arch. then when this hits 1, which is at the very top, the section is d minus the difference, which is going to be d2. Okay? And then we use that now as new section height, okay? And I think that's it. Is that true? We have an arch. The arch looks like here is much higher than this here. And here is 0.40, here is 0.15. Let's bake this and see if it's true. So I'm going to bake this, and then, oh no, actually, sorry, let me bake. What did I bake? What did I just bake? Okay, I don't know what I baked. Let me bake the console output. So the console output is this one. Let me bake it. So now we have the surface here. And I'm going to do this, and then I'm going to do distance, and that's going to be from here to here, and that's 0.40. That's what we had here. And if I go all the way to the top, I'm not sure which one of these is the section. So I think it's this one. So distance from here to here, and you can see that the distance in the C is 0.15. So I think we got it. Nice. I think we got it. Okay. So awesome. So now we have the arch with the varying thickness. Okay, very clean, very parametric, very procedural. We can tweak these things. So now this is much thicker on the top, and this is close to 0 in the bottom. That's also a kind of cool design, huh? And with that, now we're ready to take this B-rep and to start replicating it. Down in the spanning direction, okay, using data trees. Shall we take a look at that? Okay. All right. Woohoo! How's everybody holding on? Oh, I've been doing. Oh, it's been an hour and a half already. Wow, this is taking super long. Is there anybody? I still see no one. Okay. I mean, we're almost done. This was the difficult part. We just need to replicate it now and do the pipes, and that should be it basically. Thank you, Owaze. So where were we? Yeah, so some data tree magic. I want to do something here. I'm just keeping this as B-rep array, and I want to be a bit cleaner and just get the main arch. So I'm probably going to take this. I'm probably going to take this and just extract the one B-rep that I like. Because the thing is that when you sweep, sometimes the result of the sweep is not just one B-rep, it's multiple B-reps. So that's why the return type of this function is an array. But here, because everything is very controlled and is very clean, very likely this array is always going to be with one element. So we want to take just the first element out of it, you know? So yeah, okay. What are we going to call this? We'll figure out. Okay, let's get to it. Before we move on, I want to notice one thing. The return type of perform sweep, it's not one B rep is actually an array of B reps, because sometimes, depending on the parameters, if things are not perfectly aligned, etc., you may actually get multiple surfaces as opposed to one as the result of the sweep process. So that's why the return type is an array. But since here the process is much more controlled and we've taken good care of making everything programmatic and tight, it's probably going to always be just one B rep. So I want to make sure that before I start cloning this and moving them around, that instead of doing that with an array, I do it with the one single B rep that is the good result of our operation. So I'm just going to either take this, or I'm just gonna make it more verbose. Main arch B rep, okay, and that's going to be main arch surfaces, the first element of the list, okay, and this is the one that I will output here, and you're gonna notice something probably as I click run. This is going to go from, you see, instead of going from a 2D a tree with a path with two levels, it just becomes one, because instead of outputting an array, we are outputting one single element. So Grasshopper processes that in a different way, which is a bit cleaner. And then now create data tree of B rep arches. Okay, so first I'm going to create myself an output here. So that's going to be base arch curves, and I'm going to say base arch B reps. Okay, so that's going to be one. I'm going to remove this stuff here. It's getting a little clogged, and I'm going to go all the way down here and say, as usual, let's start a data tree. Let's start a data tree of B rep elements. Okay, of B rep elements, and I'm going to call this base arch. Base arch. Why do I always get stuck doing this? Base arch B reps, for example. B reps, but that's the same name that's the same name. Base arch surfaces, for example. And this is going to be a new data tree. Okay, and this is going to be of the type B rep. And then here I'm going to iterate over all the spans, and then I'm going to take the B rep, and I'm going to take main arch B rep, and I'm going to duplicate it. I'm going to duplicate the B rep, okay, so to create a copy of it, and then I'm going to move it, and then I'm going to move it in X, an amount equal to I times D, which is the width of each span, and then I'm going to create a new path, a new Grasshopper path, which is going to be equal to a new Grasshopper path with I, and then to this data tree I'm going to add this B rep that I just created at the path that I just designed. And all the way at the very end, I'm going to output here. I'm going to say base arch B reps is going to be equal to this data tree that I just generated right now. And that failed. Oh yes, sorry, because I forgot that this has to be XYZ. So that's going to be 0 and 0. Yes. And as I do this, things work well, and it looks like I have all those arches. So this one is duplicate. So I'm going to remove the console. I'm going to stop outputting that, and I'm going to copy these so that I have a dedicated one. Exactly. So it looks like we're good, except you see, except that I need to do, just like I did before, I need to add one more element to the span because we have one more arch than spans. So that's just going to be as easy as number of spans plus one here. Okay, we got this, and okay, so I think with this we are more than ready now to go ahead and then just I know we have to do the arches in the middle. Okay, so we're going to do the same process but with the arches in the middle. Just to refresh myself, MD1, MD2, MW. Okay, so we're just going to copy paste that. Okay. Okay. Wait. Okay, cool. I'm going to copy everything manually just because I don't want to copy paste things and forget to rename something and then spend half an hour debugging it. So if you don't want to get bored, just speed through this part because I'm basically going to copy paste everything and then just do like small tweaks. So I'm going to create middle arch sweep brep. So that's going to be double middle arch subparameters are going to be equal to what is the name of the middle curve? It was arch middle curve. Okay, so here dot divide by count, and I'm going to use the same number, true, and then I'm going to create an array of planes. This is going to be perpendicular frame middle arch, and this is going to be equal to arch middle curve dot get perpendicular frames. Get perpendicular frames, and main arch subparameters middle arch subparameters, and then curve another array of sections middle is going to be equal to a new curve array equal in amounts of this many elements dot length. Okay, and then double section. I'm just going to recycle this. You know what? I'm actually going to recycle some of this. So this can be sections is going to be equal to a new array. Section difference is going to be equal to MD1 minus MD2. So I'm just going to reuse these variables so that I don't have to declare them again. And then this for loop is going to be exactly the same thing because I'm going over sections. And then plane PL is going to be equal to perpendicular frame middle arch, and then this is going to be the exact same thing. The normalized height is going to be the same. New section height is going to be also the same because it's going to be new section and section difference. I'm using the same numbers. Width is going to be equal to, you see, I end up copy pasting. I should start like listening more to what I say. You see, here the danger, I should have, and I have to remember to make this MW, and then the rectangle, these two things are going to be the same. So rectangle R, new rectangle PL, PL, and this looks good to me. And here, because I already have a sweep class that has all the parameters and all the configuration that I used, I can reuse this same sweep this frame sweep variable to perform the sweep. And this, I'm going to use arch middle curve as the rail, and then the section, I'm going to use sections, and then I'm going to store that in an array. Brep middle arch surfaces is going to be equal to the result of this, and brep is going to be equal to middle arch brep. It's going to be equal to this thing here, to the first element of the list. And let's output it in the console so that we know if it's working correctly, and it looks good to me. So right now this is this is looking very large. Okay, so if I bake this, it's probably not. It's probably way too large. So distance, this is 0.38. That is very odd. You see, there's probably some copy pasting that I should not have done here. 0.358. Nope, that's not good. And distance here is going to be right, is going to be equal to 0.235. Yeah, so something is not working here. So let me take a look at what that is. It's something with the heights. So section difference is MD1, MD2. Oh, you see the copy pasting. You see, I was telling you, I'm subtracting from D1 as opposed to MD1. I knew it. So let me bake this again and make sure that it's correct. So distance here is now 0.85. Did I measure this correctly? In the Z 0.85, that's not correct. And this distance should be this distance is 0.208. Nope, still not working. Okay, so MD2. Okay, yeah, the height, because the height is not anymore the origin Z and the base point. The height difference is the normalized height difference has a different rule now. The normalized height difference is different. So we have to figure out what is H for the main arches, what is full H, and what is the difference between this point and this point. So that is where things are not, yeah. So you see, copy pasting, it never works. Okay, so let's take a look at this. So we have here at the beginning, we made this list of middle arch points. Okay, so this middle arch points is an array that has is a list that has the 3 points that we use to create the middle arch. So the first one is the one that has or we could do this numerically. Let's do this numerically. So let's say double arch base is going to be equal to base point, the C height of base point, plus, I believe it was, what was it? It was H1. Okay, so plus H1, double arch top was base point plus height of the arch plus h2. And then double arch height is going to be equal to these two. It's going to be equal to the difference between these two. This minus arch base. Okay. So that's there. And now this, instead of base point z, this is going to be arch base, and this is going to be the height of the arch. And as I do this, I don't know, things have not changed a lot visually, but I'm still going to bake this to see. Oh, sorry, I've been doing all of this. Oh, I've been doing this, all of this. Sorry, I've been doing all of this in the diagram. So yes, what I just wrote was I added these three lines here where I was computing arch base, arch top, and arch height. So the height of the middle arch, and then how high the base of the middle arch was, and how high the top of the middle arch was. And the height is the difference between those two. And then I replaced here. Now the base is this new value, arch base, and the total height of the arch is this one. Let's see if this works. So I'm going to calculate this distance, and this is 0.25. Now we're talking. And here on the right, this is 0.1 millimeters. So, okay. So this is what happens with mindless copy pasting. Hope you guys never do it, just like I did. Okay, and now let's write a data tree here, where we create a data tree, create a vrep middle arches. So data tree vrep middle arch surfaces is going to be equal to this stuff here, and then I'm going to copy this. This is going to be vrep. So number of spans, we don't want to do +1 right now. vrep is going to be equal to main arch vrep. No, middle arch vrep. We're going to duplicate this. We're going to translate it 1 times d. Path is going to be good, and then to middle arch surfaces, we're going to add this vrep here. This gives me an error, which is, what is it? 250, line 251. I can, oh yeah, the name is already in scope. So middle arch surfaces, middle arch surfs, for example, here. We're going to change that. Yes, I was just duplicating the name here with the data tree as well. And let's create an output here, middle arch curves, middle arch vreps. Okay, we need to close this so that it updates. And middle arch vreps is going to be equal to the data tree that we just created. Okay, and is that true? It is. It looks like it's true. So we now have these the middle arch vreps. They're full solids, and yep. Okay, so we're good to go. So it sounds like the only thing that is left is just to do the piping. So that's going to be hopefully super simple. Okay, let's get to it. Okay. Oh, I'm so tired. Oh. And let's finalize this. Is there such a thing as a pipe in Rhino Common? Let's take a look at that. When we say pipe, Mesh pipe, mesh create from pipe, create pipe method. Uh, brep create pipe, it's a static method, and it takes the rail, the radius, local blending, pipe cap, fit rail, absolute tolerance, angle tolerance. That's a lot of stuff. So let's take a look at local blending. Is if true local pipe radius stays constant at the ends and changes more rapidly in the middle is applied. Okay, if false, global radius is linearly blended from one end to the other, creating pipes that taper from one radius to the other. I'm not sure what this means, so we're just gonna give it a try. Also, we could just extrude a circle, you know? We could just create a circle and extrude it. Maybe that's easier. I have no idea anymore. Fit right. If a curve is a polycurve of lines and arcs, the curve is a fit and a single surface is created. Otherwise, the result is a poly surface. Yeah, I think doing a pipe is going to be an overkill here. I think doing a pipe is going to be an overkill here. Maybe we can just create like a small function that we give it a line and it gives us a surface, a pipe from line or something like that. And that could be an interesting exercise, actually. And so, because if we do extrude, but create from taper extrude, create extrusion, curve, path curve, and cap. The path to extrude along. If the true extrusion is capped with a translation of the face, we rep face. Yeah, but this belongs to B rep face. That's not what I want. Surface create extrusion method. Curve profile and direction. Construct a surface by extruding a curve along a vector. This looks good to me. This sounds better. It's just easier. I think we're going to do this as opposed to pipe. Pipe sounds like an overkill. Pipe is great if you have like a curve that is with torsion and that kind of stuff. But for a simple line, I think we're much better off here. This is probably much cheaper to do as well, computationally. Why not the same rail sweep? For the same reasons, because a sweep is a much more complex operation that takes into account the tangency, the normal of the curve, etc. And it's great if you have a curve that changes and that has torsion, but if it's just a simple line, this method is just much cleaner. It's just like one surface, you know? And probably much cheaper to compute computationally. It's going to take much, it's going to take, it's going to be much simpler for the computer to do. Now the question is, do we want to create all the surfaces and then clone them, or do we want to do them from lines? I think we want to create them and then clone them, just like we've been doing, right? Okay. So where are we going to do this? These ribs. Create the ribs data tree. we can probably we can take those lines and okay, so we're gonna do it here. We're gonna take the lines and then we're going to create a function that is going to take a line and a radius and is going to return a surface. We're going to write that ourselves too. That's probably going to be much cleaner. Yes, I think so. Yeah, and we can actually just hack this here. Yeah, we can just do it here in the middle of this code. Okay. Okay, so let me explain this, and and then I will get into why, and then I will get into doing it. Okay. Now, as I was checking the Rhino common documentation to find the piping methods, I run into brep create pipe, but it strikes me. So this is what we would have probably used in vanilla Grasshopper to create a pipe around the lines, and I think that's what we did in the previous video. But it strikes me that this operation is super complex and it's going to be probably computationally super expensive, way more than we need for just simply extruding a circle along a simple line. Create pipe is probably great if you have a curve that has a lot of twist and a lot of torsion, but for us, in such a simpler scenario, I think this is probably an overkill, and what we probably want to do is find something simpler, like for example, surface create extrusion. So create an extrusion as from just a simple profile curve and a direction vector, because at the end of the day what we have is a line, and a line is almost equal to a vector between the 2 points, the start and the end point. So this approach is probably going to be much simpler to implement, and it's probably going to be also much more lightweight computationally to do. So we're going to do as we did before. We're going to generate all the surfaces for the left ribs and the right ribs, and then we're going to clone them. Along the spanning direction. And actually, we're going to do that by going back into the code and going to where we were creating the ribs. So here, the left span ribs as lines and the right span ribs as lines. And we're going to take advantage of the fact that here we're already looping and generating these lines, etc. And we're going to insert some code here to at the same time as we are creating the lines for the ribs, to also create the surfaces, and then just like do everything in one go, you know. And we may actually take advantage of this code here as well to make things a little cleaner. And in order to do this in a much cleaner way, what I'm actually going to do is I'm going to create my own function. It's going to be a function that I'm going to call it, for example, something like pipe from line. And given a line and given the radius of the pipe, I want that function to return a surface that is going to be that extrusion. So in order to do that, I'm going to go all the way down here, and I'm going to create a new function. That function is going to return a surface object, so that's going to be surface. I'm going to give it a name, so surface, so for example, pipe from line. And then the inputs that these are going to take is going to be a line object, is going to be a double, the radius, and then that's it. I don't need anything else. Okay, so how is that going to work? Well, first of all, if what I'm going to end up using is surface extrusion, okay, so what I need to do is I will end up creating something like surface extrusion, blah, blah, blah. And then this will need the curve profile, so a circle. And then it's going to require the direction extrusion. But I don't have those yet. I have to create them. So the first thing I need to do is I need to create a vector, direction vector, and then the circle. I need to create it. I need to create a circle that is placed at the beginning of the line and whose normal is also in the direction of the line. So let me put a hole to this one. And first of all, let's say vector 3D direction is going to be equal to a vector that is formed by the point at the end of the line, so line 2, minus the point at the beginning of the line, so line from. That vector is going to be a vector that is going to be in the direction of the line and is going to have the length of this line. And the circle, we first need a plane located at the beginning of the, we need a plane that is going to be located at the beginning of the line, at line from, and whose normal is going to be perpendicular to this. So let me say plane base plane, or PL, is going to be equal to a new plane. And you see, we can create a plane from an origin and a normal. So we do have the origin, so that's going to be line from, and we also have the normal. Is this vector, this direction vector that we just created. So direction. Okay. Then the next thing is going to be circle C is going to be equal to a new circle based on that plane that we just created, so PL, and with a radius of the value that that is coming from the function, so radius. And then remember that we can't work with circles directly when we do NURBS operations, so we need to convert the circle into a curve. So that's going to be curve CRV is going to be equal to C, the circle that we created before, converted into a NURBS curve. I think now we're ready to go for this guy. So now the surface is going to be create extrusion. We have the curve profile, so that's going to be CRV, and we have the direction vector. So that is direction. And I think that's it. So this is the object that we want to return, SRF, surface. Okay, good. So let's go back now here. Let's go back to, and I'm going to copy this name because I'm going to forget it, of course. Here where we were creating the base riffs, we probably want to create here a list of surface objects called the left span surfaces. New list, blah, blah, blah. And here, and now I'm going to rewrite this a little. I'm going to put this here. I'm going to write this a little. So I'm going to say line L is going to be equal to this new line that we created here. Okay, and then I'm going to add the line to the list. Okay, so that's fine. And then now I'm going to say surface SRF is going to be equal to pipe from line, that function that I just created myself, and line, I'm going to use L, which I already have, and radius is going to be, what is it going to be? Pipe radius, yes. So we have it as an input here. So that is going to be, where is this? Pipe from line, pipe radius, okay, and then after I create that surface, I want to add it to this list left span surfaces. Add .srf. Okay, do I run this? It doesn't work. Something is broken. 146 here. Oh yeah, I forgot this here. 146. Okay, and we don't see anything here yet because we're not outputting it yet. So let me use the console to see if that, so console equals left span surfaces, all these guys. So I'm going to output there, and boom, turns out we are creating all those surfaces, and you can see all these pipes out there. So that's great. It's looking nice. And what is the next thing to do? So I'm going to remove this. I'm going to do the same thing for the right spans. So here I'm going to create another list of surfaces, and this is going to be right span surfaces, and here I'm going to create a surface S is going to be equal to pipe from line L and the radius, and then right span surfaces at S. If let me output this to the console to see if it works. Here, there you go, and then it works. We have them here, and now we're just going to use the data trees. So we're going to take advantage of all this for looping that is going on here to also create a data tree of surfaces, and we're going to apply the exact same logic that we did before. We're going to have, this tree is going to have two levels. The first one is going to be the module, so which span are we in, and the second level is going to be 0 for the left pipes and 1 for the right pipes. So let me create here a data tree of surface objects. So rib surfaces, new data tree, okay, and then surface, and then here we have the vector, left clones, we have the clones, and so here I'm going to create surface left surf clones, new list, blah blah blah, surface, okay, and then here we have the same number of lines and pipes, so we can reuse this for loop. Here we are working with the lines, but now here we're going to say surface clone S is going to be equal to wait. So wait. Yeah, it's going to be equal to left span surfaces. It's going to be equal to left span surfaces I, and that here. Something is not working. Okay, surface source, the original one is going to be this one. Okay. Now, can we take source and can we duplicate it? Can we duplicate? Yes. So duplicate shallow. Yes. So can we duplicate this? Okay. And then as we do that, we're going to say clone s dot translate, and we're going to translate it with vector v, vector that we just calculated before, and then we're going to add this to left surface clones at clone s. Okay. Something is not working. Cannot implicitly convert type geometry base to Rhino geometry surface. 191. So we're not going to be able to duplicate this. So let's try duplicate shallow. Oh, no. So I think the way to fix this is to just say we can duplicate it, but then we're going to have to cast it again into a surface object. Yes. So this method was returning a geometry-based object, which we cannot store on a surface object. We have to explicitly cast it back to the surface type. Okay, and since we're here now, so surface clone is here, left surface clone, so path indices, rib axis, so rib to rib surfaces, I can add a range, which is going to be the left surface clones path. Okay, this works. So let me rib lines. Let me here on rib surfaces add an output, and here, where is it? Rib surfaces is going to be equal to where did I have this? Where did I have this? Rib surfaces here. I'm going to output this, and it looks like, okay, so let me turn this off. Let me copy this here. Let me turn this off again. It looks like it's not working, and that I am duplicating all of these guys. This is probably, I think this is probably similar to what we did before. There's some problem with the I and the J. Yes, so here, instead of I, this is J here. Okay, so that's great. Now we have all the elements on the left, and we are now just going to finish that off with the elements on the right. So there is surface left clones. So here I'm going to copy this, and I'm going to call it right surface clones, right span ribs, so blah blah blah, and then here same thing, source. This is going to be right span surfaces, J clone, surface duplicate clone, and then right surfaces clones at there. And here we're going to right surfaces clones here. And ta-da! And it looks like everything is working correctly. And it looks like we have everything. These are the B reps, and these are the curves. These are the B reps as well, and these are the surfaces. So it looks like everything is working. So let me just do some baking so that we can see if everything works. Da-da-da, and then bake this, yes, and bake this, da-da-da, and then we're going to turn this off, and we're going to do a little bit of better shading. Oh, rendered, yes. All right, and here we go. Doo-doo-doo. Finally, yay, that was a lot, okay? Okay. Doo-doo-doo, yay, fireworks, yay. All right, oof. Ay. Okay. Oh, that was a lot. Ooh. So, okay, so we're going to finish. I'm going to finish the video. I'm going to wrap it up somehow. I'm going to wrap it up. What can I say about wrapping it up? So what we just did, and perhaps like steps forward. So what other folks could do. Okay, so how many? Okay, so so here we are. So this is the modeling of the Calatravas Umbraco building in Valencia, done in purely C# scripting. It took us a little time to get this together. It may seem a little tedious, but I think this exercise was incredible in that we were able to touch upon a lot of interesting topics and a lot of like, for example, how to create sweeps, how to manipulate data trees, how to customize the paths, how to rethink, for example, pipes, and like for a very simple situation, just like conceive them as a very simple extrusion. So I think that was a very good exercise, and I hope you guys could see the very, very fine level of detail and control that we get when we start customizing and writing these applications on our own. I can't really tell, but I'm also fairly confident that this component with its 300 milliseconds execution time is probably much, much more performative than the same code running on vanilla Grasshopper. So that's also an advantage. And very often it has happened to me in professional life when I have like very, very, really complicated models that have a lot of different geometry, and I need to do a lot of operations for like 3D printing and slicing and that kind of stuff. Writing these things in C Sharp definitely pays off. So um, I this exercise could use a lot of things. It could use a little bit of cleaning up and optimization of the code. It could use like introducing more variables. So for example, instead of using a square section, we could have done a a W section, like in the original model, in the original building. We could have trimmed the pipes so that they actually land exactly on the side of the beam, as opposed to getting into the beam. So like they do here. So if we zoom in, so here, if we zoom in, you can see that you can see how these pipes actually get into the beam. We could have worked with some intersections and to make that a bit cleaner. You see how this, for example, is not very clean. We are starting the rifts exactly at the beginning of this curve. So this is actually not a very realistic joint in the real world for execution. So perhaps like adding some kind of offset here, like we did here, would have been an interesting thing to do. But I'm going to leave all those additions to you, the viewer. If you want to pimp this exercise up and or like maybe add geometry even underneath the building, add people walking around, or like make it more fancy, or now maybe you wanna design the structure of the concrete beams that are supporting this platform. It's totally up to you. Remember that we are always open to contributions. So if you make something cool, or if you extend this exercise much further, feel free to reach out or to do a pull request on the GitHub repo and submit your code if you want to share it with the world. You can also share it with us on the Discord channel. And if you were interested in how the process that I followed to actually figure out, because I did not prepare this video at all. If you want to interested in the process that I followed to figure out how to tell the story and build this here with you, make sure you check the live streams that I used to build this, and that can probably help you even better understand how to get to know Rhino Common better. Okay, so until that, we're going to be doing more of this. So feel free to like this video, to subscribe to the channel if you want to learn more about computational design, and see you in the next video. Oh, okay. And now let me record the introduction real quick, and then we can have a small chat and Q&A before I take off. I need to leave before the shops close. I need to buy groceries. I'm out of food. Okay, so let me record the introduction. Let me bake. Am I going to bake? Am I going to bake anything here? Do I want to show this baked or not? Let's bake it. So actually, wait. So I did have it baked before. Okay. Hi, and welcome to the second part of this video series where we are modeling the Calatravas Umbraco building in Valencia. But this time, in this second video, instead of using regular... Okay, I'm starting over again. Hi, and welcome to part 2 of this series of videos where I'm modeling the Umbraco building in Valencia by Santiago Calatrava. And but in this second part, instead of using regular vanilla Grasshopper components in the visual programming language environment, what I would like to do is I would like to follow the exact same process, but reconstruct the building using C# scripting within Grasshopper in Rhino. Okay. I think this exercise, if you want to take a really quick look, there's a lot of code here, but I'm going to break down everything of what are we doing and why all this makes sense. And I think this exercise is very interesting if you are interested. It's very interesting if you're interested in learning how to supersede visual programming languages and get a bit more low-level exposure to how these things are implemented internally. This exercise will be particularly good to learn things such as, for example, customizing data tree structures in Grasshopper, how to do complex sweeps along rails in using Rhino Common, and some other abstractions that we're going to be using here for the sake of optimization. I would like to what? I would like to what? All right. Well, it's gonna be take 3 now. Hey, Shireen, good to see you. I didn't know you were there. Um, okay, so take 3. I don't know what I was saying there. I'm really tired tonight. Okay. Hi, and welcome to part 2 of this series of videos where I am modeling the Umbraco building by Santiago Calatrava in Valencia. In this second part, I would like to mimic what we did in the first one, where we only used vanilla, simple Grasshopper components, but this time I just want to implement the exact same logic within a C# scripting component. I think this is a really good exercise if you want to know a bit more and get more exposure about how to do these things at a lower level and how all those Grasshopper components are actually implemented using this thing called Rhino Common, which is the library, the geometry library that runs underneath Rhino and Grasshopper. This exercise will be very useful for you if you're trying to learn things such as, for example, how to customize your data tree structures, the ones that are coming outside of as an output of the component. If you want to learn more about, for example, how to create a complex like a sweep around the rail with variable sections, how to go back between simple structs and NURBS curves geometry, and a lot of other small features that we will have to do to implement this code. It's gonna take a little bit of time to break down because I really want to explain everything that I did here. But you're invited to follow me along, and otherwise remember that there are links here in the description to the source code that I will be using in case you want to have it on the side. And that's pretty much it. Let's get going. Woohoo! And we're done. Okay, that took some time. How are you guys doing? Oh, I'm out of water. Okay. Woohoo! Let me save this. Okay, and this is gone. I don't need to save any changes. I don't need to save this. Okay, I'm open to 5 or 10 minutes of Q&A if you guys are up to. I'm gonna take a quick bathroom break, so I'll be right back, and then we can You can start posting questions if you want on the chat. Okay, I'll be right back. Okay. Owazi has two questions. Which are those two questions? I'm open to questions. Whoa, okay, that's a lot. Okay, Reynaldo. Is there any way to perform the structural analysis of the structure, like exploring the geometry to exporting the geometry to a structural analysis software, or maybe use the Caramba extension is easier? What do you think? Well, there is, of course. One of the nice things about this exercise is that we have worked in order to get to the surfaces and the B-reps. We did have to generate the curves, okay? Which means that we have two types of geometry families. So we have all the axes, so all the lines that define the centers of the elements, and then we have like, which is what I would use, for example, for an architectural project to define where are the elements, like this, how things are measured, right? But then on top of that, we also have the B-reps, which is what I would use for representation, like for creating visualizations, renderings, etc. Those are not very useful for 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 structural analysis, for example, but the lines and the segments are. The only trick here is that structural analysis software usually does that cannot take NURBS geometry as an input. Structural analysis software usually relies on straight line segments for the frames that represent the elements on a structure. So what we will need to do is we will need to change this model a little bit so that, for example, the NURBS curves that represent the arches are not NURBS, but is a discretized polyline. So it's like a lot of small straight segments, and so that, and we will need to do that as well, because since the section of the structure is variable, very often what we do in structural analysis is that we model one beam that has a lot of tiny segments, and if the beam is variable section, then what we do is like we apply different sections to each one of those tiny lines, which are to mimic this idea of the section becoming smaller. So something that could be done if you want to use this model for structural analysis is to, on a next step, take the I'm gonna say it. Take the NURBS curve and discretize it into segments, small ones, and then that's what you feed to your software analysis. And actually, what I would recommend in our case is that instead of just randomly choosing like I don't know, I'm going to divide this curve in like however many segments and make those a polyline. Instead of that, I would recommend splitting at the points where the ribs actually land on the arches, because remember that in structural analysis you need to have the frames, the bars always need to end in a node. So it's very convenient if you discretize the big arch in nodes that correspond exactly where the ribs connect to those arches. That way, you are sure that all the stresses and all the forces from the ribs are going to be landing correctly on the arches and are going to be transmitted down into the foundation. That's the only thing that I could suggest. Owasi, can you please help recreate the complete functionality of the graph mapper with all its graph types in C# with only number sliders, completely get rid of the tactile interface? Graph mapper. So graph mapper is the one that is two dimensionals. It's two dimensions, right? Graph mapper. Oh no, it's the one that. Oh wait, let me look that up. Did I close? Yes, I closed this. Which one is the graph mapper? It's the one that gives you like a function, like a visual function. Okay. Here, graph mapper. Oh, I see. So you want to recreate this in a C# component with only number sliders and no tactile interface? Well, the thing with the tactile interface is that it gives you a lot of control of the curve. So, but there are ways where we could simplify this. Yes, we could simplify this. And then just have, like, for example, with sliders, just have the X and Y location of each one of these nodes, and then have one per different component for each one of the graph types here. So the conic curve, the Perlin noise, etc. It could be done. It's just that I find this actually, I don't like components that require you to touch them, like this one. But I do like, because like I want to be able to control them parametrically. So it is true that I would like this component to have some hooks so that I can control the height of this guy and the height of this guy with some sliders. But what I do like about these UI components is that they give you like a very clean visual clue about what's happening. So mimicking that in C# would not be straightforward. So maybe we can think about this for some component in the future. Yeah. And then another one, guide us towards some resources to decompile the component to do the same. It will make the outputs for multi-object optimization engines like Wallacey plugins so much more cooler. I mean, there are resources to just create custom layouts for C# components. You will not be able to do this in a C# script component. You would have to compile your own native Grasshopper plugins, but there are resources out there, so you can take a look at those. Maybe we can do one of these exercises at some point here. Benson, when there are multiple ways to achieve the same results, how do you decide which way to use? Is there a tool to measure the cost of certain operations in C#? Well, there are. So if we open the file that we were working on, I was using, where is this? I have this thing called the profiler on, and the profiler tells me how much time one component takes to execute. So that's a way of measuring. That's a way of measuring how computationally expensive your operations are. Now, I have this here, but what's not intuitive is to say, for example, okay, all this other vanilla code all together as an aggregate, how many resources does it take? You know, that I don't think we can know. There's no such a thing as a profiler for a group of components. That would actually be quite nice, in fact. but this is one measure of computationally expensive. How do I choose between methods? Honestly, I do it based on experience. So I've done a lot of this, so I know that some methods are a bit more lightweight than others, and but there are some general rules of thumb. So for example, when when an operation is very generic, so when an operation tries to satisfy as many input conditions and as many forms of geometry and as many types of inputs, that's usually a more expensive operation, just because since it has to adapt to so many situations, it takes resources to decide and to come up with a data structure that is able to accommodate um, all these situations. Um, that was, for example, the situation that we run into today with the piping. That method was really good because you can pipe anything, you can pipe over any curve. But for us, since we only needed like a very simple straight extrusion, then it was much easier to do it manually with a curve and a vector. And it's also much more lightweight because it doesn't have to accommodate for all these other situations, you know? Um, Sometimes you just want whatever gets the job done really fast. So if you're in a hurry, you have a deadline, you just want whatever it's. So actually, I mean, I don't really use Grasshopper very often lately, but sometimes when I do, I just do vanilla Grasshopper because it's just like, oh, okay, whatever. Just this. I just need to prototype something. Um, it's only when I want things to be publishable, to put them online, to create Grasshopper plugins, or I really need performance, that I put the extra effort in scripting things so that I can then cash out on those advantages down the road. But it's mostly based on experience, I think, at least in my case. I don't know. Fernando, plans for C# classes. Plans for C# classes. Well, I I was planning on doing a full playlist here in the channel at some point. Let's learn C# from scratch on its own, without Grasshopper, without anything, and then let's learn the basics, and then let's learn how C# lives in other environments such as Grasshopper, Unity, Dynamo, VVV, whatever you want to do, you know. Um, so that's gonna happen at some point. It's not going to happen immediately because I want to do an intro to Grasshopper, and that's probably what I'm going to do the next full Saturday. I'm just going to be recording introduction to plain Grasshopper videos. Um, but yeah, those are my plans right now. I also think that through doing these exercises like we did today, those are a good introduction to C#. It's not a formal one, but it can give you guys an idea of how things work. And Andres Obregon, how to code the kangaroo remove duplicate points. That's actually a fairly simple, that could be a geometry gem. Just like have a list of points and remove duplicates. Huh, okay. We could probably do that, I think. Because it's just as simple as like a for loop that checks the distance to other points. And when you find one that is under a threshold, then you just remove that from the list, you know? Okay, I'm gonna write it down because that's a good idea. And it's a simple geometry gem that we could do. There are there are a couple native Grasshopper components that do that, I think. Like I was actually I was actually talking to a collaborator who has implemented that component. Oh, here, closest points could call duplicates. So this is exactly that. It just takes a list of points and a tolerance, and then it removes those points by either leaving one, removing them all, or computing the average. So yep, we can take a look at that. That's a pretty simple gem to do. All right, so okay, so are we ready for the weekend then? Is it that time? I'm very excited. I have a cooking project for this weekend, for tomorrow, so that's gonna be awesome. I'm gonna cook a really, really large paella tomorrow. Okay, well, if there are no more questions, I think I'm gonna take off. Thank you very much for sticking around. Thank you very much for sharing your Saturday with me. I think this was a lot of fun. And I think next week we're gonna go ahead and recording your start recording like an introduction to playing Grasshopper series of videos. Okay, so stay tuned if you want some more. Okay, have a good weekend. Thank you very much.